Name?
Adrian.
Name? Okay. Okay, so I'm going to start on announcements. The chapter 2. The second chapter 2 homework is due on Wednesday. The first chapter 3 homework will be due the week after. The second one will be due on the 11th of March. There'll be a delay because of the exam. We will have our chapter 2 quiz on Wednesday in lecture. And the chapter 1 and 2 exam will be on Monday. We have a lab today. We will not have a lab next week on Monday because we have the exam. But if you do need to make up a lab or something, you can do it then. So any questions about any of that? Like on the quizzes and the lab and the exams, you get one sheet of notes that you can use for reference for like formulas and such. So, quick review of objects and Newton's first law, which we discussed last time. So an object will remain at rest or in uniform motion in a straight line unless it's acted on by some external unbalanced force. Balanced forces have equal magnitude in opposite directions, and an external force is a force applied to the entire object or system. So if an asteroid is traveling at 3,000 kilometers per second, if it's not affected by external forces, what will its speed be in 2 years? Well, asteroid is not affected by external forces, so its velocity is not going to change, so its speed will be exactly the same. So it will be traveling at 3,000 kilometers per second. No external force, no change in velocity. So Newton's second law is that acceleration is force over mass. And it is most commonly written as force equals mass times acceleration. So the acceleration of any object is proportional to the force. The bigger the force you apply to an object, the more acceleration it will have, and inversely proportional to the mass. The larger the mass of the object, the less acceleration it will have. So acceleration is proportional to force over mass. We define our units such that acceleration equals force over mass. So force equals mass times acceleration. And if you want to find mass, mass is force over acceleration. So it is most commonly written as force equals mass times acceleration, because the new concept here is force, also because that fits on one line. So the original situation, if you have constant force, you get a constant acceleration. You have some force F applied to some mass M, you get an acceleration A. If you double the force, you double the acceleration. But if we, again, just apply the same force, but double the mass, we get half the acceleration. More force, more acceleration. More mass, less acceleration. So the force here is the total force or the net force of all the external forces, which is likely the sum of 2 or more forces. The mass and acceleration are concerning the whole system, and units-wise, force is in newtons, mass is in kilograms, acceleration is meters per second squared. So kilograms times meters per second squared is equal to newtons. So a newton, the unit of force, is 1 kilogram meter per second squared. And because no one wants to write out kilogram meter per second squared all over and over again, we call it a newton. The unit of force in US customary units is the pound. It's the force caused by, it's pound. There's also a mass pound, the whole, they're a mess. So here's an example of net force and total mass. So here we have two forces. Force one is to the left. So the positive direction is to the right here. Force one is to the left, and it is 5 newtons, so it is negative 5 newtons. Force two is to the right, and it is 8 newtons, so it is positive 8 newtons. The two blocks are connected by a string, so we can treat them as one complete system. And mass one is 1 kilogram, mass two is 1 kilogram. So the total mass is going to be 2 kilograms. The forces are applied to blocks that are connected by a string. They're resting on a frictionless surface, so we don't need to worry about friction. And we don't need to worry. We really are only interested in the forces horizontally here. The vertical forces all cancel out. So what's the acceleration of the system? Well, we know that mass one and mass two are both 1 kilogram, and that force one is minus 5 newtons and force two is plus 8 newtons. So if we add the forces, we get 8 newtons minus 5 newtons, and then divide by the mass, the sum of the masses, divided by 1 kilogram plus 1 kilogram, we get 3 newtons divided by 2 kilograms, or 1.5 meters per second squared. So if you want to find the acceleration, it's total force over the mass. So here is an example. We have a 10 kilogram block on a frictionless surface. It's pushed to the left with a 200 Newton force. What is its acceleration? So I'll give you a minute or so to work on that. So remember, and then so force equals mass times acceleration. We want to find acceleration. We divide both sides by mass. We get acceleration as force divided by mass. So 200 newtons divided by 10 kilograms gives us an acceleration of 20 meters per second, and the direction is to the left. Which I think I forgot to put in there, but 20 meters per second to the left. Because I gave a direction in the description. Here we have a 20 kilogram mass that accelerates at 28.8 meters per second squared. So what's the total force on this mass? So force equals mass times acceleration. We know the acceleration. We know the mass. So mass is 20 kilograms. 20 kilograms times 28.8 meters per second squared gives us 576 meters. That's the force required to accelerate a 20 kilogram mass at 28.8 meters per second squared. So the total force or the net force on this object is 576 meters. Here we have a cart pulled by a 1,440 Newton force that accelerates at 12 meters per second squared. The question is, what is the mass of this cart? And remember, the other way you can rearrange this equation is you can solve for mass, and you find that mass is force over acceleration. So force is mass times acceleration. Therefore, you can divide both sides by acceleration. Mass is force over acceleration. So mass is 1,440 newtons divided by 12 meters per second squared, which is 120 kilograms. So here we have a 30 Newton force placed on a mass that's starting at rest. And after 3 seconds, the mass achieves a velocity of 9 meters per second. So the question is, what is the mass of this object? So for this, you're going to need to use the equation for acceleration from last chapter, where acceleration is final velocity minus initial velocity over time. And then you'll also need to use force equals mass times acceleration. So I'll give you a minute or so to work on this. So the first thing we need to do is figure out the acceleration of this object. Acceleration is final velocity minus initial velocity over time. Our final velocity is 9 meters per second. Our initial velocity is 0 because we started at rest. The time is 3 seconds. So 9 meters per second minus 0 over 3 seconds gives us an acceleration of 3 meters per second squared. Now that we know the acceleration and we know the force, we can find the mass. Force equals mass times acceleration. If we solve for mass equals force over acceleration. The mass is 30 newtons divided by 3 meters per second squared, which gives us a mass of 10 kilograms. People are still writing. Okay. So oops, that got duplicated. I was copying something and copied the problem twice. So we already did that one. So I'll just skip over it. So let's talk about the difference between mass and weight. Mass is the amount of matter present. Your mass does not change unless you gain or lose material. Weight is related to the amount of force from gravity. Your weight changes depending on how strong gravity is. So if you went to somewhere where gravity was less, your weight would be less. So, classic example is if you go to the moon, your weight will be a sixth of what it is on Earth. Because gravity on the moon is a sixth as strong as Earth. But that also means there's some easy ways to lose weight without actually losing mass. Gravity gets weaker the further away you get from the center of the Earth. So if you ride an elevator up to the top of a very tall building, you will weigh ever so slightly less. Once you ride the elevator back down, you will weigh the same amount you did before. So it's not really a solution. But that is a way to lose weight. So, on Earth, weight is mass times the acceleration due to gravity. So weight is sort of a special case of force equals mass times acceleration. Your weight is your mass times g, the acceleration due to gravity. G equals 9.80 meters per second squared. So if the force of gravity changes, like between Earth and the moon, your weight will change. Or say if you went to Mars, your weight on Mars would be less. I can't remember how much weaker gravity is on Mars. I think it's like a third. But I could be remembering wrong. So yeah. But oh no, it's like 30% weaker. So it would be like 70% of it on it. Well, the moon is like a sixth of the gravity on it. So your weight will change with the changing pull of gravity, like between Earth and the moon. So here's an example of computing weight. If you have, so weight will be in newtons, mass is in kilograms. Kilograms or grams are a measure of mass. Newtons is a measure of weight. Weight is the force of gravity on you. So what is the weight of a 2.45 kilogram mass on Earth and on the moon? So here, we're going to use weight equals mass times g, and g will change. On Earth, g is 9.8 meters per second squared. On the moon, it's a sixth of that, 9.8 meters per second squared divided by 6. So 2.45 kilograms times 9.8 meters per second squared gives you 24 newtons, which is 5.4 pounds. And on the moon, 2.45 kilograms times 9.8 meters per second squared divided by 6 gives you 4 newtons. The force would be a sixth of that on Earth. And that's 0.9 pounds. So if you weigh 150 pounds on Earth, on the moon, you'd weigh 25 pounds. But if you mass 100 kilograms, the moon, you'll still mass 100 kilograms. So the acceleration due to gravity is independent of your mass. So both force and mass get doubled, and so G remains constant. Because your acceleration is force over mass, but your force is proportional to your mass. So if you double the mass, you double the force, and the acceleration remains constant. And this is actually true no matter where. Gravity is always, the acceleration due to gravity is always independent of the mass. That acceleration can vary as you get further or closer to a source of gravity, but it is always proportional. The force is always proportional to your mass, and so the acceleration is always independent of mass. So, if a 10 kilogram mass is dropped and only affected by gravity, it will accelerate at g equal to 9.8 meters per second squared. So how much force does gravity place on this mass? This is asking what is the weight of a 10 kilogram mass. So I'll let you work on that for a little bit. It's fairly straightforward. Remember, force equals mass times acceleration. So force equals mass times acceleration. The force of gravity is the weight. It's mass times g. So 10 kilograms times 9.8 meters per second squared is 98. And you can see how that's almost 100 newtons. Because g is almost 10, a good rough approximation of the weight of something is just 10 times its mass. So, that means 100. This would have a weight of around 10 newtons. 100 gram mass would have a weight of 1 newton. That's a good rough approximation. You're only off by a couple percent. So here, this is a little more complicated of a problem. We have a 4 million kilogram helicopter, 4 times 10 to the 6 kilograms. It's accelerating upwards at 3.5 meters per second squared. So the forces on it, it's got the forces of the rotors pushing upwards, the force of gravity, its weight pulling downwards. And the question is, how much force do the rotors produce in order to counteract gravity and accelerate it upwards against gravity at 3.5 meters per second? So we know the net force, the total force will be up. You would expect the force of the rotors to be greater than the weight. And the total force is going to be the force of the rotors minus the weight, if you take up as positive. And that will equal the mass times the acceleration. So, the net force is mass times acceleration. And that's going to be the force of the rotors minus the weight. So I'll let you think about that for a little while. So the force, if we solve for the force of the rotors by adding weight to both sides, we get mass times acceleration plus weight. Weight is just mass times g. So the force of the rotors is going to be mass times acceleration plus mg. So that's mass, 4 times 10 to the 6 kilograms times 3.5 meters per second squared, plus 4 times 10 to the 6 kilograms times 9.8 meters per second squared, which is 1.4 times 10 to the 7 newtons plus 3.92 times 10 to the 7 newtons, which comes out to 5.32 times 10 to the 7 newtons, or 53.2 million newtons. Now, another common force is friction. The friction is a force that resists the movement of two materials that are sliding against each other. So it occurs, it resists relative motion whenever two materials are in contact with each other. You can think about it like the goal of friction is to keep things from sliding. And there's always friction. There's friction found in all states, solids, liquids, and gases. We're only going to talk about like contact friction, the friction between just a surface, two surfaces sliding against each other. And now we modify things to change their friction. Sometimes we want more friction. So like right now, you're going out and driving in your car, you would like to maximize friction because you don't want your tires to slip. So we can do things like put sand on ice to increase the friction. So being as we're in the Chicago area, the general solution in Chicago is to eliminate the ice by salting everything because there was a mayor who lost an election for failing to clear the streets. In other cases, we want less friction. So inside your car, you have oil to prevent friction in your motor from wasting the energy that you'd like to go to your tire, to your tires. So motor oil reduces friction, prevents heat and buildup from that friction. The friction generally turns, energy into heat, which can be bad. So in your car, you have things that are designed to have minimal friction, where you have lubricated parts and such, ball bearings, things like that. And you have things designed to have maximal friction, like your brakes. So there's two main types of friction. Static friction is the friction force between two surfaces when they aren't moving relative to each other. This is the force between your shoes and the ground, the force between the tires of your car and the ground, if things are going right. The force that keeps things from starting to move if they're sitting still on a table. So if the two surfaces are not moving relative to each other, like when you're walking, your feet don't move relative to the ground, that's static friction. If they are moving or sliding, that's kinetic friction, kinetic for movement. The kinetic friction is the friction that occurs when there is relative motion between the surfaces in contact. And the two phases of friction are a little bit different because static friction is a force that is as big as it needs to be to keep the object from moving, from sliding. But there's an upper limit. And then kinetic friction is trying to keep the object, to stop the object from sliding. So it's always the same amount, more or less. But in general, the important thing to remember is that kinetic friction is generally weaker than static friction. Usually it takes less force to keep something moving than to start it moving. It's also why if your tires start slipping, you have less control because the kinetic friction between your tires and the road is less than the static friction when they're not slipping between the tires and the road. It takes less force to keep something moving than it does to start it moving. That's sort of the general thought. And the way we describe the strength of friction is with coefficients of friction. They're written with a Greek letter mu, which looks like it's the same thing that's used in the abbreviation for micro. It looks like a U with a bar on the front. Coefficients of friction are dimensionless quantities that are used to characterize particular contact situations. And any particular contact situation will have a coefficient of static friction and a coefficient of kinetic friction. And almost always, the coefficient of kinetic friction is less than the static friction. I don't think I've ever seen a case where kinetic was greater than static. I've seen some where they're so close as to be the same. But so generally, coefficient of static friction is greater than the coefficient of kinetic friction. I'm not going to say that's always the case because I'm certain there's some bizarre case where that's not true, but pretty much every case you'll ever see that is the case. So here are some examples. We're not going to go into the actual formula used to calculate the strength of friction. That's beyond this class. I'll tell you the coefficient of these coefficients of friction relate the force pressing between the surfaces. The harder you squeeze two surfaces together, the stronger the friction force, to the force of friction. So like your brakes, when you step on your brakes, the brake pads squeeze to increase the friction. So some examples of friction between materials. So aluminum on aluminum, static friction is 1.9, kinetic friction is 1.4. Aluminum on steel, on the other hand, slides a lot more easily. Static friction is only 0.61, kinetic friction is 0.47. Steel on steel, dry is 0.75 and 0.48. Lubricated, 0.12 and 0.07. Teflon on steel is 0.04 and 0.04. Teflon on Teflon is 0.04 and 0.04. Teflon is super slippery. That's one of the nice things about it. It also doesn't react with just about anything. So, it's useful. Rubber on concrete. Dry rubber on concrete, 1.2 for static, 0.85 for kinetic. Wet, it's about 0.8 for static, 0.6 for kinetic. Wood on wood, about 0.58 for static, 0.4 for kinetic, and then lubricated ball bearings is less than 0.01 for both. So, if friction provides a drag force of 20 newtons for a 30-kilogram cart, how much force do I have to apply to get an acceleration of 5 meters per second squared? So the general idea here is you'll figure out the total force from the acceleration and the mass, and then you'll work out how much force has to be applied, assuming there is a drag force from friction, which will be negative. It's going to oppose the motion of the car. So, the force applied is being opposed by the force of friction, and those combined give you the total force, which gives you the acceleration. So the total force and the net force is going to be mass times acceleration. But the net force is equal to the applied force minus the friction force. So the applied force is going to be mass times acceleration plus the friction force. So 30 kilograms times 5 meters per second squared plus 20 newtons. 150 newtons needed is your net force or your total force. And then you have to add an extra 20 newtons to overcome friction. So you need to apply 170. Here we have a 20 kilogram block that's pushed along the floor at 4.5 meters per second. Got a constant velocity by a horizontal force of 490 newtons. So it takes 490 newtons to push this block along the floor with a net force of 0. So that 490 newtons perfectly balances the friction force while it's sliding. If the block stops, will 490 newtons be likely to start it moving again? What do you guys think? Yes or no? So I can push this block along the ground with 490 newtons of force. But if I stop and let it come to a stop, will 490 newtons of force be enough to get it started moving again? Am I seeing yeses? That is the force needed to overcome friction, but it's the force needed to overcome sliding or kinetic friction. And static friction is usually stronger than kinetic friction, so it is unlikely that that will be enough. You'll probably need some more force. You probably experience this when you're pushing something. Once it starts moving, you don't have to push as hard. So usually static friction is stronger than kinetic friction, so it usually takes more force to get something moving than it does to keep it moving. Now, we've now covered Newton's first law and Newton's second law. So let's talk about Newton's third law of motion. Newton's third law of motion. So Newton's first law and Newton's second law are both talking about what happens to an object when a force is applied. Newton's third law of motion talks about how forces work between objects. Newton's third law says for every action, there's an equal and opposite reaction. What that means is that actually all forces come in pairs. For every force, whenever an object exerts a force on a second object, that second object exerts an equally sized but in the opposite direction force on the first object. So if I push on the wall pushes back on me with an equal and opposite force. And you use this every day. You use this to enter this room. Because when you walk, you push on the ground backwards, and so the ground pushes you forward. You are, that's how we move. So every action has an equal and opposite reaction. All forces come in pairs between two objects. So if you pull on something, it pulls back on you with an equal and opposite force. Now, the acceleration won't necessarily be the same because the masses of the two objects can be very different. So for example, if I drop my pen, it is applying a force. It has a force applied to it from Earth due to gravity, and there is an equal and opposite force applied to the Earth from my pen. However, the acceleration of the Earth is imperceptible while my pen falls at 9.8 meters per second squared, because the mass of my pen is much, 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 much less than the mass of the Earth. So the general thing is that force 1 equals minus force 2, or the force of 1 on 2 is equal to minus the force of 2 on 1. And if there aren't any forces involved, you get mass 1 times acceleration 1 equals minus mass 2 times acceleration. So if the mass of one of the objects is much, much larger than the other, it doesn't really move, while the other seems to get all the acceleration. So an example is jet propulsion. Exhaust gases are pushed in one direction, and the balloon is pushed in the opposite direction. I need to pick my balloon up. Or a rocket, for example, or gravity. If you jump from a table, you will accelerate towards Earth, but in reality, also the Earth accelerates towards you. But the amount that the Earth accelerates towards you is so small, it's not perceivable. Because you have a small mass, so you get a huge acceleration, while Earth has a large mass, and so you get a very small acceleration. But mass 1 times acceleration 1 does equal minus mass 2 times acceleration. So the force of 1 on 2 equals minus the force of 2 on 1. So here this weight is pushing down on the table with a force of 9.8 newtons, and the table is pushing up on it with an equal and opposite force of 9.8 newtons. So you experience Newton's laws all the time. So for example, if you're in a car that's going around a corner, friction on the tires provides the necessary centripetal acceleration, and the passengers will continue to travel in a straight line until they, in the original one, so that's the second law, the passengers will continue to travel ahead in the original direction as the car turns until the door or the seatbelt or something impacts the passenger and applies a force. That's Newton's first law. And as the car turns, you push against the door equally pushes against you. That is Newton's third law. So if I apply 21 newtons of force downwards on a tabletop, what force does the tabletop apply on me? Well, yep, and it's up. Force of 1 on 2 is minus force of 2 on 1. The force of the table on the hand is minus the force of the hand on the table. So minus 21 newtons down is 21 newtons up. Same size force, opposite direction. But it's not, and they don't cancel out because they're applied to different objects. But Newton's third law is why we only have to worry about external forces, because all the forces inside a system will cancel out because they all come in pairs. So here we have two masses. We have mass 1, a 1 kilogram mass, applies a force on mass 2, which is a 2 kilogram mass, that causes mass 2 to accelerate away at 1 meter per second squared to the left. So minus 1 meter per second squared. What force does mass 2 apply to mass 1? And what acceleration does mass 1 achieve? So here, the force of 1 on 2 is going to be mass 2 times acceleration 2. So that's 2 kilograms times the minus 1 meters per second squared, so minus 2 newtons. The force of 1 on 2 is minus the force of 2 on 1. So the force of 2 on 1 is minus the force of 1 on 2, which is minus 2 newtons. It's going to be 2 newtons to the right. The force mass 2 applies to mass 1 is 2 newtons to the right. Force on of 2 on 1 is mass 1 times acceleration 1. So acceleration 1 is force of 2 on 1 over mass 1. So 2 newtons divided by 1 kilogram. Acceleration 1 is 2 meters per second squared. questions about that. Just remember, forces come in pairs. And if you push on something, it pushes back on you with an equal and opposite force. And the same is that if you pull on something, it pulls back on you with an equal and opposite force. So here we have a car, it suddenly accelerates at 3 meters per second squared to the north. What force does the car apply to a 100 kilogram driver? Assuming the driver ends up accelerating at that same speed. And what force does the 100 kilogram driver apply to the car? So I'll give you guys a minute or so to work out this. So we want to figure out what force the car is applying to a 100 kilogram driver. The force of the car on the driver is going to be the mass of the driver times the acceleration. So that's 100 kilograms times 3 meters per second squared. Well, that's 300 newtons to the north. The force of the driver on the car is minus the force of the car on the driver. So that'll be minus 300 newtons. So 300 newtons to the south. So if the car is pushing you forward with 300 newtons, you are pushing back on the car with 300. And here we have a 12 kilogram mass sitting on a table at rest. So the question here is, what force does the table have on the mass, and what force does the mass have on the table? So here's sort of a diagram. Nothing is moving, so the net force on everything is going to be 0. The weight of the forces on the box, there's the weight pulling the box down, and the force of the table on the box pushing up, and then the force of the table on the box, the force of the box on the table is pointing down. So the net force on the box is 0. So the force of the table on the box minus the box's weight equals 0. The weight is mg. The force of the table on the box minus mg equals 0. So the force of the table on the box is mg. So that's 12 kilograms times 9.8 meters per second squared. It's 117.6 newtons. So the force of the table on the box, rounded to the appropriate number of significant figures, is 12 newtons. I'm sorry, 120 newtons. Because this only has 2 significant figures. The force of the box on the table will be minus the force of the table on the box. So the force of the table on the box is 120 newtons up. The force of the box on the table is going to be minus 117.6 newtons. So minus 117.6 newtons, or 117.6 newtons down, minus 120 newtons. It will be 120 newtons down. And we're going to stop there. managed to get a good amount ahead. That's okay. So I'm going to stop sharing. I'm going to